Hi!
Hi. Huh?
So I recently saw this video on how the lighting in Paper Mario 64 worked. It's way simpler than it looks. You just offset the sprite a little and then you make it light or dark and you have your effects. So I was like, what if I made this in GameMaker? And I did. Here's the final result. It supports multiple lights and you can go in front of the lights and behind them. There are smooth transitions when you switch between these modes or if you go away from the lights. And I'm gonna take you through the whole process of how I did this step by step. You can download the full final project from the link in the description and let's get started. When you draw a sprite in GameMaker, it goes through the default shader. It pulls the sprite from texture page pixel by pixel and outputs that. Now you can make your own shader to take control over that process and do whatever you want. That's how we're gonna do this lighting. Now shaders in GameMaker are written in GLSL, not in GML, so you can't just pull any variable from any object, but you can pass values from GML into your GLSL shader using uniforms. You're gonna see them in action later. For the base project, I have a player that walks around and one light to begin with. It's just simple code for movement and for depth sorting. For this technique, you need to make sure that you're using separate sprites for the player's left and right animations, because doing the image X scale flipping method is not gonna work with the shader because it's also gonna flip the lighting. The next thing I did is making a shader asset, and for this we only need to work within the fragment shader. First of all, we need two uniforms to pass data from GML into this shader. One is a 2D vector for storing the distance to the nearest light, so it has an X value and a Y value. And the other is a 2D vector that stores the size of 1 pixel on the texture page of the sprite. So say you offset the texture coordinates by this amount, it means you're gonna offset it by 1 pixel on the texture page. In the player object, we go to the create event first. I'm gonna make some variables here. This is the radius of the lights, so beyond 300 pixels the lights won't have any effect on the player. And this is a struct with the X and Y distance to the nearest light. Then for the shader, we are simply taking the handlers of the uniforms that we made in the shader, and it's through these handlers that we can pass values from GML into the shader. Now the end step event is where we look for the nearest light. So right now I'm just gonna look for the nearest light instance and we're gonna work on multiple lights later in the video. And now if we have found a light, we're gonna get its normalized distance based on the max distance that we made in the create event, which is 300. So normalizing it means that instead of it being a value from 0 to 300 and more, it will be normalized from 0 to 1. So it essentially becomes like a multiplier that you can use in the shader. Now the draw event is where we use the shader. So here first of all, I'm gonna set the shader to the one we made and then use this function to pass the X and Y distance to the light into the distance uniform. And then we need to get the size of the texture pixel or the texel of the sprite's texture page. So we first get the texture page for the sprite. Then we make a local struct to store the X and Y texel sizes. And then we use that to pass the texel sizes into the texel uniform that we created. Then we draw the player itself using drawSelf, and at the end we reset the shader to the default shader. In this section we're gonna write the shader code for when the light is behind the player. So for this, the first thing you need to do is go into the shader and open the fragment shader. Now before the main function, I'm gonna make a 2D vector which is gonna have a value of 8. This is basically a multiplier for how intense the effect is, and we're just gonna multiply the texture coordinates with this, and 8 is the value that I found that works best, but you can experiment with this later on. Now this default line here is just taking the color of the pixel from the texture page using its current position, and it directly takes that and outputs it to the screen, and that's how you see the sprite. But I'm gonna disable the output for now and just store it in a custom vector, which needs to be a vec4 to store the red, green, blue and alpha values. Then I'll make a 2D vector that stores the new position from where we want to pull the color information. So this is actually for the rim lighting. It just takes the current position of the pixel and it adds the distance uniform multiplied with the texel size, so it moves 1 pixel at a time on the texture, and then that is multiplied with the movement vector, which is, like I said, just a multiplier to increase or decrease the intensity of the effect. Then I'm gonna make a vec4 to store the color information of the new pixel. We use the texture 2D function again to get a color from the texture page, and we're gonna use the new position that we calculated. What I want to do is, wherever the sprite is not transparent, I want that to subtract the color from the original color so it becomes darker there. And because we are shifting the sprite, this means that the transparent areas are gonna become the part of the sprite that appear lit, and you get the effect. For that, we need a subtraction value, which we're gonna make as a simple float, which is just a singular value that will be taken from the alpha of the pixel that we just picked. Then I'm gonna multiply that subtraction value by 0.4, otherwise it would make the shadow area completely black, which we don't want. Then we subtract that value from the RGB of the color, and to do that we have to make it a vec3, so it subtracts from the 3 values. And then we apply the final color to GL frag color, which is the actual output of the pixel. So if you run the game, you're gonna see the lighting effect is working. The basic effect we saw in the video is implemented, but of course there's still a lot more to do to make this complete. The first thing I wanna do now is make the shadow bluer, because if you see in real life, shadows are cooler. So we can do this after the subtraction by increasing just the blue component of the color by the subtraction value. And once you do that, you're gonna see that the shadowy area is more blue now and it looks way nicer than it did before. Right now, if you go behind the light, you're gonna see the effect is still active, and it does sort of look cool if you want it to look like the light is underneath the player, but in this case I want it to appear as if the light is in front of the player and you see a slight shadow behind the player. So let's work on that. In the shader, I'm gonna make a vec2 multiplier here, which for both components takes the sign of the y distance and flips it. This just means that the vector will be -1 and -1 if we are above the light, and it'll be 1 and 1 if we are below the light. So we can essentially use this to invert any values that we want to invert if we are above the light. And then we also need a Boolean value, which is actually a float, so it works as a multiplier, but it can only be 0 or 1, where 0 means we are below the light and 1 means we are above the light. Now where we calculate the new position, I'm gonna factor in the new multiplier with the distance and the other values. Then for the subtraction value, we need to invert the way it's calculated if we are above the light, because we now want the transparent parts of the sprite to subtract from the color and the opaque part of the sprite to be the part that would be visible. If you run the game with this and walk above the light, you can see that the effect is basically inverted now. Instead of seeing a rim lighting, you now see a shadow behind the player sprite, and most of it appears lit. So both parts of our lighting are implemented now, but there's still a lot to do. Like, we need to smooth the lighting as you get away from the lamp. Then we need to add a smoother transition between the two lighting modes. And then we need to add support for multiple lights. For the lighting range smoothing, in the shader, I'm gonna make a constant float, which is how early it starts to smooth out the lighting. Then in the main function, after calculating the subtraction value, I'm gonna make a float to get the length of the distance vector. Then I want to calculate a float value that will just add extra subtraction if you're far away enough from the light. The main value here is the distance with 1 subtracted from it, and since we are clamping it between 0 and range, it means we only get the distance effect once we are beyond the max radius of the light. So we get that value and then we divide it by the range to normalize it between 0 and 1. And then we change the subtraction value. It'll pick the minimum from either 1 or the subtraction value with the out of range value added to it. So the use of the min function just means that the value can't go above 1. Run the game with this and you will notice the smoothing of the lighting as you walk away from the light. You can experiment with the range value to get the kind of smoothing effect that you want. Now we want a smooth transition when going from one lighting mode to the other. In the shader just after the code that we added, I'm gonna make a new float that again just needs to increase the subtraction across the board when it detects we are in the middle of a transition. You can see I'm using max with a value of 0, so it means the value can't go below 0. Then the value itself is based on the positive value of the y distance being normalized and then being inverted. We then again change the subtraction value with the clamp function so it doesn't go out of the 0 to 1 range, with the actual value being the subtraction value with the smooth value added to it. Now run the game with this and you're gonna see the transition is smooth now. The range of how long it takes to transition smoothly is controlled by this 0.1 value, so you can change this to experiment with a longer transition. Now one issue I noticed is that if you stand right in the middle of the light, slightly above it, you're gonna become unlit when in this situation you should be fully lit. So a simple fix for this was multiplying the smooth value here by the distance vector's length, so the transition is more visible away from the light, and closer to the light it's not as smooth, which is not a perfect solution, but at least it gets rid of that issue, and now in the center of the light you are fully lit. Now this is the fun part, because so far we've just been working with one light, but now we're gonna add support for multiple lights and make the transition between them as smooth as possible. Basically, we're gonna look for all the lights within the player's range and find the nearest two. We get 2 points, one that is the closest light and one that is in the middle of the two closest lights. Then we do some maths to find an interpolation value depending on the player's distances to the lights, which will tell us where on this line the light should come from. So to implement this, I went into the player's create event, and here we make a DS list to store all the lights that we find every frame. And then we add the cleanup event, and here destroy the list so it doesn't stay in memory when the player instance doesn't exist anymore. Then in the end step event, I'm gonna remove the old code for finding the nearest light. And first of all, I'm gonna reset the light distance to 1 so it's completely dark if there's no lights. And then for finding lights, let's first clear the list of any existing lights from the previous frame and then run the collision circle list function so we find all the light instances that are within the player's range. Just a tiny bit more by multiplying it with 1.5. We look for obj light, we store them in the lights list, and make sure you set the last argument to true so you get the closest lights in the list first. Then I'm gonna make a local struct just to store the final position of the light that we're gonna use as the source. Now if the function found any lights at all, we are first gonna go and store the position of that first light into the struct, and in the case of just one light, the block ends here. But if we do find more than one light, then we need to average the position between the two closest lights so that walking between them is smooth. So in that case, we get the second light from the list, and then we get the distance from the player to the first light, and then the distance from the player to the second light. Then we get the difference between both distances and divide it by 30. This basically slows down the transition, and you can experiment with this value later on. Then I'm just inverting that value and clamping it between 0 and 1. So this is actually our interpolation value that helps us find where on that line we need to be. Now I'm making another local struct with x and y positions. This is the point that is exactly in the middle of the two lights. After that, we calculate the final position using the lerp function to interpolate between the closest light's position and the middle point between the two lights, using the inverted value from before as the interpolation value. So this is gonna give us the position of the source of the light that we are gonna use. And then after closing this block where we found more than one light, we do this, which is kind of the same as before. We are normalizing the distance between the player and the light source. So multiple lights are gonna work now, but just so we can see how the system works and where the actual light source is, let's go into the player's draw event, and at the end I'm gonna use the red color to draw a circle at the point where the player considers the light to be coming from. And now if you run the game with multiple lights placed in a row, you will see that the transition is working perfectly, and the red dot shows you how it's interpolating between their positions with all the math that we just did. Now I do see if you go outside of a light's range, you're still lit a bit. So going back into the end step code where we reset the distance to 1 and 1, it would be better to set it to 2 so we are not lit in the dark anymore. And with that, the issue is gone. Away from any lights, you are completely unlit. Now go ahead and experiment with this code, experiment with the shader, and I hope you can make this fit into your game. And that's it for this video. There's a lot you can add to this as well, like shadows, because you do have the position of the nearest light, but maybe that's for another video. I hope you have a nice day and I'll see you in the next one. Bye.